Hello everybody, welcome back to MSE 210. So this is kind of an extension of the lesson we've been doing, but then I thought I'll make this a separate video because it might be useful for more than just the students of MSE 210. With that in mind, so the main focus here is to understand the hypothesis testing for mean for the cases where the standard deviation of the population is known and for cases where the standard deviation is unknown. Right? So those are essentially two different cases. The main concept is kind of like illustrated through an example at the bottom. So generally when we talk about hypothesis, it's kind of a guess or some claim regarding the population. So there could be multiple hypotheses, but within the scope of statistics, we're generally talking about some claim related to some population parameter. So an example here is you and your friend basically come across a pick and place robot. Maybe you built it or maybe your friend did. But then your friend basically claims that he or she believes that the robot will take at least like 15 seconds to pick the load from one point and place it to the other. You, on the other hand, contend his or her claim is untrue. So what you do is your counterclaim is that it's going to be less than 15 seconds. So those are kind of opposite cases. So this could be an example of a wager where you're having some bet, or you could have any combination, or it could be another population that you're examining. But this is kind of the general or very, very broad idea dealing with when you're dealing with statistical hypothesis testing. So we are going to consider cases where both the standard deviation of the population is known. In this case, it's known to be 0.5 seconds, and for the case where the standard deviation of the population is unknown, right? So let's kind of, before we proceed and then do this calculation, so we're going to mainly do this or visualize this on RStudio, basically, which uses R on the inside. Before we do that, let's kind of like very, very quickly look at an overview of what the hypothesis testing is. So the main idea is we're going to be looking, just like to recap what statistical inferences are, what is hypothesis testing, and then what are the two hypotheses we generally use for testing, and then what are the possible sources of error, and then how we deal with it. So very briefly, so the statistical inference, is basically some decision or some estimate of the population parameter from samples. So this could be either you're finding a bound on the true population parameter, or you could have some hypothesis where you think either the population parameter is below a particular threshold or above, or maybe you can also see that it's equal to that value. So then we'll examine how likely that event is, or how likely your hypothesis is to be true. So then when you're doing hypothesis testing, generally the hypothesis is a statement or a claim regarding this population parameter, and then hypothesis testing is we are evaluating the or the hypothesis based on some sample that we collected or some experiment that we have done. So generally we have two hypotheses we begin with. So we have what's known as the null hypothesis. This is the primary or the default hypothesis. So generally null hypothesis will state that the parameter is equal to some particular value, or it could be that it's greater than equal to some value or less than equal to some value. So generally the null hypothesis would include the equality case. So if you notice, we have this equality or less than equal to or greater than equal to some value over here. The alternate hypothesis is going to be the entire kind of like the domain or area which is not encompassed by the null hypothesis. So in this case, if you have that the null hypothesis is that parameter is equal to some value, in that case your alternate hypothesis would be that the parameter is not equal to the value, so it's either like greater than or less than that value. In the case where you assume that the null hypothesis is that the parameter is greater than some particular value, in that case your alternate hypothesis would be the same parameter is less than that value, and similarly for less than equal to case. So generally what we do is we only reject the null hypothesis or fail to reject it. So we generally don't have the concept of accepting the null hypothesis. So that's kind of a semantic. Generally, if you have enough data, so that's kind of a default assumption that you would accept the null hypothesis, but generally that's not normally done, or you don't, at least in statistics, say that accept the null hypothesis, unless you want everybody laughing at you. So we look at some possible errors when you're dealing with it. So there could be a case where the null hypothesis is actually correct, and the test indicate that we need to reject the null hypothesis. This is known as a type 1 error, and then we would call this probability as alpha. And then what we also have is a type 2 error where the H naught, or the null hypothesis, is false in actuality, and then the testing actually fails to reject the null hypothesis. So generally, the hypothesis testing is typically used to calculate the probability of type 1 error, where we say if when alpha is very, very small, we typically reject it. So generally, or more often than not, we are not really considering the case of the beta error. So with that, let's go back, just revisit the problem. So this is what we're going to be doing, and then we're going to try to look at first the case where the standard deviation of the population is known, and then we'll try to simulate this using RStudio. So here we have RStudio fired up. So this is what we're doing. So I copied the problem. So this is going to be the case where the standard deviation is basically known. So the idea here is, again, this is the problem and this is the experiments that you have done, and then you get these numbers over here. So let's do this setup. So generally for the random things, we basically set some seed value so that our problem is basically repeatable. So I'm going to just run this one step at a time. So then we have given the sample. So let's calculate the sample parameters that we have here. So here the standard mean, or the sample mean, is 14, and then the standard deviation from the sample is 1.5. Right, so this is not too bad. So now the claim is, we haven't really answered this question, is the true population parameter, which is the time to pick and place, is it really greater than 15 seconds, or could it be greater than equal to 15 seconds, or could it be less than 15 seconds? So from this, it appears that it might be less, but then the question is 1 second a good enough time? So from here, the sample standard deviation is this much. So we have to kind of think about it a little bit more. So let's try to simulate what will happen if you have a very, very large population, and then you are basically randomly selecting, and essentially you're doing the same number of counts. So in this case, it's going to be 5. And then you picked 5 samples and then calculated the average time. So we're going to assume that the times are actually distributed normally. So the way we do that is, since we know the standard deviations, we're going to assume that's that. And then to evaluate the claim of the null hypothesis, so let's assume that it's indeed 15 seconds and then see what the population is. And then because the claim is actually that it's greater than equal to 15 seconds, so what we're going to do is we're going to just have another mean which is a little bit higher than the null hypothesis, so just to see what the effect would be if you look at a higher mean. So we run this and then we can plot the population. So this is just generating the population here, and then we can plot the population. So as a essentially like a cumulative plot. So essentially this is the command. So this is the population, is where everything is stored, and then I'm basically creating a histogram here. So then it looks good enough. So let's kind of add the direction, the other mean, and then also the sample mean that we get. So the sample mean is shown here in red, which is 14. And then if you had a different mean and then completely different like essentially the same standard deviation, so you can basically get something similar to the dashed line. So it's kind of evident that it's more likely that if you choose the smaller value, so of the mean here, that's when you're most likely to be close to the close to proving, or rather to put it better, to not being able to disprove the null hypothesis. So generally we'll focus on the least smaller value of the null hypothesis. So here's we have, so this doesn't really tell the story, because what we've done is we're basically looking at the sample mean. So this isn't like a fair comparison, so we have to start sampling from this normal distribution and then calculate the sampling distribution. So once again, I'm going to use the R power here. So this basically just this command is used to pick up n representative samples. I'm going to pick the sample size is going to be equal to the number of experiments. In my case it was 5, so I'm going to keep that as is, and then I'm going to pick about 15,000 samples from the normal distribution that we have, and then generate the new sampling distribution. So these are the code that is needed, and then I'm also going to do the case where I'm essentially kind of doing the same thing for the other population as well. So with that, let's run this, and then we can plot the new distribution here, which kind of looks like this. So now the solid line or the solid gray box kind of represents the equality case, so which is going to be the case where the standard deviation is equal to the mean of this population is equal to 15. So you would basically get a distribution of your sampling mean like this, and then if it was indeed higher, so basically in this case I assumed it was one standard deviation higher, so in the case it's 15.5, you'd get the dash deviation. So once again it stands that you like if you increase this to the higher extreme of the null hypothesis, you're going to actually reduce the likelihood of it happening, but nonetheless it visualizes to show how the plot actually looks. So now the central limit theorem basically says that if you have a sample size, so then your so the central limit theorem basically says that the sample mean is distributed as a normal distribution with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of the sample size. So essentially, to put it in words, so it will be a normal distribution with mu and then a standard deviation of sigma divided by square root of n sample, or in which case, in this case, we have used n experiment here. So let's actually see if this is true. So I'm going to plot both the solid and the dashed line. So notice that it more or less fits. So this kind of makes sense. So since this line is very far away, so you don't have too many samples, so we're going to basically zoom, kind of like ignoring the box, so that we'll essentially just end up with having the sample distribution. So with that, let's do the plot here. So in that case, this is the x bar, like the normalized value we get. So essentially what I'm doing is I'm going to transform this to a standard normal distribution. So the way I do that is I'm going to subtract the mean of this population and then scale it by the sigma divided by square root of n. So we do that. So this is the new normal x bar norm we get, and then we do the same thing, and then we can repeat. And then what happens is, because I'm compressing both of those, the null hypothesis value and then the for the mean actually greater than 15 would kind of collapse to the same standard deviation with a mean of 0, but then just that the the sample mean would change position. So the solid line basically represents the case where the population mean is equal to 15. The dashed line is what you would get when the standard mean is sample mean is greater than 15. So it kind of like shifts a little bit. So let's kind of like zoom in here in the plot. So I'm just going to change the axis. So if I zoom in around where this is, so if I zoom from -5 to 4, so this is what I get. So how would I calculate this probability? So I'm going to basically need to have to fill in this area. So what I'll basically do is essentially fill in this area, and then if I can calculate this probability, and this probability is very, very small, then I know that there is a very low chance that the null hypothesis is actually true. If the probability here is very large, then there is a chance that the null hypothesis might actually be true, and I can't actually reject it. So the other way to think about it is, if the null hypothesis is actually true, I'm likely to get a sample mean equal to this value, which is about 4.47 here that we get from that we noted down here, 4.472. The probability of actually getting a sample mean equal to this value is given by this area, and then we can calculate this as the cumulative probability from -infinity to up to this point. So you'll basically look at the cumulative probability table. So this basically looks and then concludes the case where we know the standard deviation. So now we will switch gears and look at the case where we don't know the standard deviation of the population. So this is the same exact problem. Except that now we do not know the standard deviation of the population, right? So this makes things a little bit interesting. So we're going to do again the same visualization. So I'm going to clear everything first and then kind of like redo this. So where I have loaded the library, and then it's okay to use the same seed here. We can change it, doesn't really matter. Once again, I'm going to calculate the population parameter, and then this really hasn't, or the sample parameter hasn't really changed. So now we need to sample the population, and then since we don't know the standard deviations, we're going to generate kind of a range of population where the mean is fixed at 15, and then we'll check, just as a check, we'll pick one where the mean is greater. But then more importantly, we're going to look at a range of standard deviation. So what I've done here is I've basically chosen the sigma to be 0.5 and then 0.5 times 4 and 0.5 times 16. Right? I just use this as a factor to scale up my kind of like the standard position of my standard deviation. Right? I could keep going, I could go all the way to infinity, but then my computer probably wouldn't be able to solve it numerically. So this is just like for demonstration purpose. Right, so we have this, and then I'm going to generate this bunch of population. So this is all the data that's generated. So now I'm going to generate all of my populations in a loop where I have the mean fixed to 15, and then we'll have one more mean which is a little bit higher by one standard deviation, just to show or illustrate how it's going to look. And more importantly, we are going to pick the mean the standard deviation to be 0.5, and then 0.5 times 4 is 2, and then we have 16, 0.5 times 16 is going to be 8. So we're going to pick and then create the population. So we are basically going to do the two parameters. So the first parameter is with the mu equal to the given mu, and then the second population parameter is a case where the population mean is a little bit higher by one standard deviation. So this would correspond to the higher case of my null hypothesis. So I'll generate this population. So once again, I can visualize this. I just have a new library here which allows me to plot the population beside each other. So if I do that and then plot my population, so this is my population distribution. So the one in solid is the case where the mean is exactly equal to 15, and then the dashed line is the mean greater than 15. So this just covers the range for my null hypothesis. So this is the case where the sigma is small, 0.5. This is the case where it's 2, and then this is the case where it's 8. So notice that as I increase, the standard deviation, the population spreads out. So all of these are put to this. Doesn't look like it's scaling, but you should kind of like look more closely at the y-axis here. So this y-axis is about 0.8, this is 0.2 and 0.05, and then you notice that the x-axis also scales. Right? What's actually happening is because the sigma scales, your population height basically decreases, and then the population spreads out. And so now this the red line, which corresponds to mean, is getting kind of like closer to the middle. So it gets more and more likely that the sample you got, the null hypothesis may not be untrue. Right? So we need to come up with a way to actually solve this problem, and then you can actually imagine going all the way to sigma equal to 0.1, 0.001 here, and then similarly here sigma equal to 10, 100. You can go to infinity, right? You shouldn't go to infinity, but in principle you can pick any high value of sigma, and then this could still be a potential population because we don't know the standard deviation. Right, so now let's see if we can do the same sampling problem. So I'm going to assume that I kind of have this population here and then pick 5 samples and then see how the distribution is going to look. Do the same thing for here and here. So again, this is the same kind of code, just that I'm doing it in a loop to look at the different standard deviation. So if I did that, so this is how the population has been generated, and then I can visualize the distribution again plotted as a grid. So notice that when the sigma is 0.5, my 14 is actually seems to be well outside of the distribution. So it seems unlikely that the null hypothesis is true. But if my population sigma is higher at 2, so then the probability, the red line, which corresponds to the null hypothesis, the red line, which corresponds to the sample mean, kind of seems to be kind of aligning or kind of going into the middle of the distribution, so it becomes more and more likely that you might have gotten a mean. Again, so if you go to 8, so it seems to be almost very close to the middle of the distribution. Again, so what I've done is, because the dashed line is one standard deviation away, so it just gives you a representation. So that means that the population could either be the solid, or it could be anywhere in the direction of the dashed line, right? So if you had a higher mean, it basically keeps shifting to the right. Right, so let's look at this. So this is the sample that we get. So now this is not looking great, right? So now you don't know, and then potentially if sigma goes to infinity, then you can't really, there is no way you can actually disprove the null hypothesis, right? So anybody, you say, hey, the probability looks smaller, and then the person proposing the null hypothesis would kind of like scratch their head and say, you know what, just try sigma equal to 8. That doesn't work. Try sigma equal to 16, 64, right? You can keep increasing, and then eventually you notice that the sample you can cover, and then this will kind of like whatever the sample is, it could be the sample might have a mean very low, but you could still pick a large enough sigma that it starts to come inside the distribution of possible mean. So that means this is not looking good. So we can't directly use the center limit theorem without using the mean, without knowing the standard deviation, and we also are aware that the population distribution tends to become wider and wider as the mean could or the standard deviation increases. So we have to still normalize the population, and the best tool that we have is to normalize it with respect to the sample standard deviation, right? We are still going to use something very similar to the center limit theorem, so where you're going to divide that by the square root of the sample size. In this case, it's n experiment. But then what we're doing is, we are dividing this by the sample standard deviation. So we're going to do the same thing here, and then I've actually already generated that for the population when I did this. So I basically calculated the normalized mean, which is the mean divided by the square root of whatever the sample distribution that we get for the sample. And then we did the same thing for the other sample with the higher null hypothesis on the higher side. So here is what we're going to do. So I'm basically going to be plotting the histogram, again doing the same thing for all of the means. So if I did that and then plotted the dashed line, so notice that for the sigma equal to 0.5, I would, because it gets normalized, I get a distribution here. For sigma equal to 2, sigma equal to 8. So all of that look very similar, and then the red line represents where the sample, the experiment would be in the case of the null hypothesis, and then the dashed line kind of gives you the direction in which this would actually shift relative to the mean that we get. So now if you look at all of this population, so all of these are actually identical. So what we have to do is we can actually no longer fit the regular normal distribution here. So this is actually shifted. So what we need to do is we need to superimpose what's known as a t distribution. So I'm going to pick the sigma equal to 0.5, doesn't really matter which one I do, and then I'll superimpose the t distribution. So notice that it actually is a very good match, and then we can do the same thing that we did before. So if I can get the probability from minus infinity to up to this red line, so that will give me the likelihood that my null hypothesis is true based on the and what is the likelihood that if the null hypothesis had been true, I would get a sample mean corresponding to the red line, which in some ways actually gives you an likelihood of how likely the null hypothesis is true, although that is semantically incorrect, right? Thinking about it. So this basically concludes our mini video or mini lecture over here. And then what we did was, just to quickly recap, so we were essentially looking at hypothesis testing. So we are understanding the hypothesis testing for the mean of the sample, and then how it relates to the population mean for the cases where the population standard deviation is known, and for the case where it's unknown. And then we did this using RStudio, and then we did a simple demonstration. So the take home from here is this slide where I've compared the two cases side by side. So if you know the standard deviation of the population, So what you do is you can normalize all of your data with respect to the standard deviation of the population using central limit theorem directly. In case the standard deviation is unknown, then you have to still normalize, but then you normalize with respect to the standard deviation of the sample, which kind of makes the tail a little bit longer. So notice that the tail here is a little bit higher. This goes almost to 0. This one is going further up, right? So you can kind of look at it and then get an idea of how this actually looks. And then in this case, we basically use the student t distribution. Again, the student t distribution is used when you're having a smaller sample size, and then small is kind of a relative term, but generally a rule of thumb is if your sample size is less than 30, and you would use the student t distribution. And the point to note is that the underlying assumption is that the population actually has a standard distribution or a normal distribution. So it may not be a standard normal distribution. So it could have a mean and a unknown population standard deviation. So this basically concludes our video, and then thank you for watching and have a great time. Bye.